going to discuss question number 43 of the assignment which I gave you. So what we have to do, there is a spherical shell which is charged, and now it is having an additional charge at its center. So this is the case when there is no charge at the center. So this case we have already done when a spherical shell is charged, and to find out the electric field, that we have already done. And now what they are saying, that suppose there is a charged sphere at the center, or they can say there is a point charge placed at the center. Method will be the same. So now let us suppose the sphere which we are placing at the center, it is having a charge q only. Now in the first part we have to find out the surface charge densities at the inner surface and at the outer surface. Okay. So in this question, first we have to use the concept of electrostatic induction. So suppose this charge is the positive charge which is given to this metallic sphere. So if this is plus q charge, due to induction on the inner surface of the shell, some charge will be induced which will be equal to q only. So that means this inner shell, it will acquire minus q charge due to electrostatic induction. Now on the outer surface, already some positive charge is there which is capital Q, and now due to induction some additional charge which will be equal to q only. See, due to this positive charge, in this conducting part electrons are getting attracted, so the inner surface it will accumulate negative charge, and because electrons are moving inward, so on this outer surface there will be some positive charge due to induction. So this charge is the additional charge which we have already given. Now due to induction, plus q charge will also be there. So the total charge on the outer surface, that becomes the earlier charge plus charge due to induction. So radii we have already been given. The inner radius is r1, outer radius is r2. So now we can easily find out the surface charge densities, because surface charge density is charge upon surface area. So inner surface has got a charge minus q, and its surface area will be 4 pi r1 square. So this will be the surface charge density of the inner surface. Now using the same concept for outer surface, charge on outer surface is capital Q plus Q. This charge was originally given, and this charge is due to induction due to the charge at the center only, and surface area of the outer surface will be 4 pi r2 square. So this is the surface charge density of outer surface. Okay. Now in the second part we have to find out the electric field at a point which is inside the shell, and electric field at a point which is in interior of the shell. Now let us find out electric field at point P. See, in the previous case when we discussed about spherical shell, there was not any charge at the center, but now there is some charge at the center as well. So that means now the results are going to be changed. So we will be proceeding as we did in the previous cases. That means we have to use the Gauss theorem. So for using Gauss theorem, the first step, we have to assume a Gaussian surface. So for point P, I have assumed this Gaussian surface which is passing through this point P. It is closed as well as it is symmetric. So now I will be doing this numerical in brief, because I am assuming that you have already done the electric field due to a spherical shell. So the first part we have done, first step we have done, we have assumed the Gaussian surface. Now as we know, we have to find out the flux. So flux by definition in case of spherical symmetries, it comes out to be E into 4 pi r square, where r is what? It is the radius of Gaussian surface. And then we find out the flux using Gauss law. So Gauss law states that the flux passing through a Gaussian surface is 1 upon epsilon naught times net charge enclosed. So how much charge is enclosed? So in earlier case, in the previous case, there was not any charge at the center. So for the point which is inside the Gaussian surface, inside the shell, electric field used to be 0 because there was not any charge. But now, while calculating the flux using Gauss law, you can't place this Q to be 0 because inside the Gaussian surface there is some charge which is equal to Q. So this flux will become Q upon epsilon naught. This is equation number 2. And as you know, the next step is to compare these two. So on comparing, I will get E into 4 pi r square is equals to Q upon epsilon naught. So E becomes 1 upon 4 pi epsilon naught Q upon r square. You can see that this outer charge, the additional charge capital Q, it is not having any effect because that charge is on the surface only. So the electric field at this point is only being produced by the charge, the additional charge which we have placed at the center only. Okay. So this is how we'll find out electric field at point P. Now let us understand how much electric field will be at point Q. So you must be knowing the result, that what should be the result at point Q, because this point Q is lying inside the conducting part of the shell. See, this is the shell, so this much part is the conducting part, and we know the electric field inside a conductor is 0. So no doubt at point Q electric field is going to be 0, but we have to prove it. So let us see how to prove this, that electric field at point Q is going to be 0. Find out the field at point Q. Again we will be assuming a Gaussian surface. So even in this case, this Gaussian surface will be a sphere. So it is symmetric, it is closed, and it is passing through the point where we have to find out electric field. And suppose the radius of this Gaussian surface is r only. Okay. Now again we will be following the same steps. So we have assumed the Gaussian surface. Next step, as we know, it is the flux by definition, and for spherical symmetry it always comes out to be E into 4 pi r square. What is the next step? The next step is to find out the flux using Gauss theorem. So Gauss law states flux is 1 upon epsilon naught times the net charge enclosed in the surface. So at the center or at that metallic sphere we are having plus Q charge, and as we discussed in the first part of the question, that due to induction the inner surface will get minus Q charge. Yes. Now let us find out the total charge inside the Gaussian surface. So this is the Gaussian surface. Inside the Gaussian surface we are having this inner surface which is having a charge minus Q, and this positively charged sphere which is having a charge plus Q. So what will be the net charge? So net charge will be 0 only, because this is plus Q and this is minus Q. So if this charge is 0, that means the flux by Gauss theorem it becomes 0 only. So this is equation number 2. As you know, next step is to compare the results. So E into 4 pi r square equal to 0, which gives us electric field to be 0. And the same thing was expected because this point was lying in interior of the conducting part. So electric field has to be 0 at this point. Now one additional point I am considering. Suppose there is a point R which is lying outside the sphere. Then what will be the electric field at that point? So in this case, again we will be proceeding in the same manner. So again we have to consider Gaussian surface which will be a sphere only. Now we don't require this. So now this is our Gaussian surface. Suppose its radius is r. So first part, finding out the flux using definition, so that will become E into 4 pi r square. Next step, finding out the flux using Gauss law. So let us solve this step now. Net charge we require. Okay, so charges are the outer surface, it is having a charge Q plus Q. Capital Q was the additional charge given and this Q was due to induction only. Okay, so let us find out the net charge now. So net charge will be, the outer one is having Q plus Q. This is outer one but it is lying inside the Gaussian surface. So I have to consider all the charges which are lying inside the Gaussian surface. So first charge is this one, Q plus Q. Then this inner surface. Inner surface is having a charge minus Q. Then we are having this charge sphere which is having a charge plus Q. So now you calculate the net charge. This Q and Q will cancel out and the net charge, it becomes capital Q plus Q. Okay. So now the flux will be written as 1 upon epsilon naught times of capital Q plus small q. This is equation number 2. Clear? Now comparing the results, we will be getting that E into 4 pi r square is equals to Q plus Q upon epsilon naught, which gives us that electric field is 1 upon 4 pi epsilon naught Q plus Q upon r square. Not a big deal. See, in the previous cases when we didn't have any charge at the center, the result was 1 upon 4 pi epsilon naught Q upon r square only. But now we are having an additional charge. So you can also understand this relation by principle of superposition, which states that electric field at any point will be the sum of electric field due to individual charges. So this charge on the surface, it produces an electric field 1 upon 4 pi epsilon naught Q upon r square. Now because there is one more point charge or one more sphere at the center, so it will also be producing its electric field. That is why the net electric field will become Q plus Q upon r square with the constant.